So as you may have noticed, writing down a system of equations can be a somewhat cumbersome task. You may have also noticed that most of the interesting information that is conveyed by the system is actually carried solely by the numerical data rather than the symbols. So to condense some of the notation, we have a shorthand representation for an m by n system of equations. So we're going to start out with an m by n linear system. So we have m equations, which give us m rows of equations, and we have n unknowns, which are going to give us n columns. We also have a column on the right-hand side of the equal sign, which we're going to call the augmentation. The augmented matrix is the m by n plus 1 rectangular array. So there are n columns of coefficients coming from our m equations together with the augmentation column on the right-hand side. The vertical column is simply a placeholder to keep track of where the equal signs used to be. The entries to the left of this vertical line, these A's, they form an m by n matrix called the coefficient matrix, and the entries on the right, as I mentioned previously, are the augmentation. So let's do an example. If we take the linear system, negative x plus y equals 1, negative 2x plus y equals minus 1, then this system corresponds to the augmented matrix. So now that we have this shorthand system of representing a linear system, we want to develop a dictionary between systems and augmented matrices. So here are some phrases that we will use interchangeably. The solution to a linear system and solution to an augmented matrix, solution space to a linear system, and solution space to an augmented matrix. Equivalent linear system and equivalent augmented matrix. So normally, we won't specify whether we're talking about the linear system or the augmented matrix. We will simply use the words solution, solution space, and equivalent when it's clear from context that we're talking about a specific system. As a shorthand, if A is the augmented matrix of a system, and B is the augmented matrix of an equivalent system, then we write A, a tilde, and B to represent that A and B are equivalent augmented matrices. That is, they represent equivalent linear systems. The next piece of our dictionary is rows and columns. So in our augmented matrix, we have rows which correspond to equations. It's very natural to talk about columns of our matrix. The jth column corresponds to all of the terms that are multiplied by the jth unknown. Using our dictionary, we can translate our operations on systems to operations on augmented matrices. We call these operations the elementary row operations. The first one is scaling. When we scale an equation, we multiply each of the coefficients by a non-zero real number, as well as the term on the right-hand side. So when we scale a row, we multiply all of the entries in that row by a non-zero real number. Here's an example. If we would like to scale the first row of the matrix by 2, then we can represent this by using a tilde with a 2R1 over the tilde. This tells us we're scaling the first row by 2, and we will obtain an equivalent matrix. Our next operation is interchange. So when we interchange two equations, that corresponds to interchanging row I and row J in the augmented matrix. Again, we get an equivalent augmented matrix, and we denote this operation with a shorthand Ri, left-right arrow, Rj. For example, if we want to interchange rows 1 and 2, we can indicate this in a shorthand with R1, left-right arrow R2, over a tilde, the augmented matrix with top row, -2, 1, -1, and bottom row, -1, 1, 1. Finally, we can encode replacement. So we indicate that we have replaced row J by row J plus the scaled row I using the symbols Rj plus CRI maps to Rj. That is, we replace row J by the row whose entries are AJ1 plus CAI1, AJ2 plus CAI2, all the way down to AJN plus CAIN, and in the augmentation column, BJ plus CBI. So let's work an example to get a good feel for how this works. If we want to replace row 2 by R2 minus 2 times row 1, we would get this augmented matrix is equal to the matrix. Now, if we would like to solve our system, next add row 2 to row 1. So in the top row, we get -1 plus 0, 1 plus -1, and 1 plus -3. The first one obviously is -1. The second entry is 0. The third entry is -2. So finally, we can scale the first row by -1 and scale the second row also by -1. So now we can see that we have a decoupled system. If we translate this decoupled system back into two equations, the top equation says x times 1 plus 0 times y is equal to 2. The bottom equation tells us 0x plus 1y is equal to 3. That is, our solution is x equals 2, y equals 3. So now that we have a dictionary between our linear systems and our augmented matrices, we'll see how to use these new objects to solve linear systems in the next video.